All right. So how many of you are taking physics now? Almost all of you, right? Except the 10th graders. So what is a vector? Well, in mathematics and science, there's two kinds of quantities. There's a scalar quantity and a vector quantity. You guys can just follow on the notes. And of course, you guys in physics, you guys know the difference, right? A scalar only has magnitude, whereas a vector has magnitude and direction. So, you guys in physics, give me some examples of scalars.
Speed.
Speed, okay, good. Wait, you guys are in physics, right?
Distance.
Distance, okay. I'm not going to write that down though. What about mass? Is mass a scalar? Yeah, otherwise I wouldn't write it here. What about work? Did you guys study work yet? It's a scalar, right? Work doesn't have direction. Oh boy. What about vector quantity? A vector quantity has magnitude and direction. So we're talking about like velocity, acceleration. Now what's the difference between velocity and speed? Some of you are wondering. Well, that's why you need to take physics. Speed is the magnitude of the velocity. Acceleration, which of course means force. And one of the more important vectors, torque. Did you guys learn torque yet? What's that? Really? You guys didn't learn torque? Whoa. It's the ability of something to twist something. Anyway, so since a vector has magnitude and direction, the best way to represent it is with an arrow. So the length of the arrow is the magnitude, and the direction it's pointing is the direction. So what we're going to do today is we're going to learn the basic properties of computations of vectors. So if this is vector v, now in textbooks, vectors are denoted by bold-faced letters, right? In physics, bold-faced. But it's really humbug to draw it, so normally what we do is you just put a V with an arrow on it. That means it's a vector. If you don't put the arrow above it, then it's not a vector. So let's say this is vector V. How would you draw 2 times vector V? I mean, if you just have to guess. If this is vector V, how would you draw 2 times vector V? You make it twice as long, but pointing in the same direction, so it would look something like this. Yeah. There, 2 times vector v. How would you draw negative 1/3 vector v? I mean, if you just had to take a guess. Make it 1/3 as long, point in the opposite direction. So, if this is vector v, 1/3 would be about that, and then it's got to point in the opposite direction, so something like this. Now, the thing about vectors is, you can move vectors all over the place. As long as they have the same magnitude and the same direction, then it's the same vector. So it doesn't matter if this vector is here, it's the same vector. Okay, so to multiply a vector times the constant, easy, right? What about adding vectors? Hope you guys remember something from physics. If this is vector A, okay, here's vector A, and vector B looks like this, how would you draw vector A plus B? Okay, you guys in physics should know this. If you didn't take physics, then you got to learn this. And then next year in physics, you get dominate. So what you do is you take vector A, again, here's vector A, see, same length, pointing in the same direction, okay? And then you take the tail of the second vector. So this is what we're trying to draw. We're trying to draw vector A plus B. So you draw vector A, the first vector, then you take the tail of the second one and you put it at the head of the first one, so like that. So this is A and this is B. And then you draw a new vector that goes from the tail of A to the head of B, like this. This is A. Why am I writing it again? It's right there. So this is A and this is B. That's vector A plus B. That's how you add vectors together. You guys in physics know this, right? Now, this is a really important skill now. So if I give you three vectors, like all connected, you should be able to tell me what plus what equals what. See how this plus this equals that. Okay, but what if I make the arrows pointing different directions, like this, this, and that? Okay, so why don't we call this A, B, and C? So looking at this, what plus what equals what? A plus B equals C. That's right. A plus B equals C. This is a very important skill. See? That's not right. That's not right. It's B plus C equal A. No wonder some of you went, what is he talking about? Right? Because look, this plus this equals that. See how the new factor goes from the tail of the first one to the head of the second one? So you have to be able to look at that and be able to tell what plus what equals what. Then that way you understand vector addition. And then of course, if you can add two vectors together, then you can subtract two vectors. Because vector subtraction is defined to be A plus negative B. All right, so what if I tell you, okay, here's vector A, here's vector B. Draw me A minus B. So you take A, so you make it the same length, pointing in the same direction, and then you gotta add to that negative B. So if this is B, negative B has the same length, except point in the opposite direction. So it's gonna look like that. And remember, you gotta put it at the head of this one, so it's gonna look like that. So this is A, this is negative B, and then you add them. So you draw a new vector that goes from the tail to the head there. Go! That is A minus B. So those are the basic operations of vectors right there. Multiply by a constant, addition, subtraction. Yeah, well, Mr. Park, what about the multiplication? Did you guys learn vector multiplication in physics? Well, there's two kinds of multiplication. So we're going to wait on that until the next time. And we're going to learn it one at a time because the second one takes a while to absorb. So there's two kinds of, I'm just going to tell you, but I'm not going to tell you how to do it. One type of vector multiplication is like this. It's called the dot product. See, because it's a dot. The other kind of vector multiplication is called the cross product. See how clever they use the two symbols for multiplication? See, but the thing is, when you multiply these two, you're going to get a scalar out of it, like work. In fact, this is how you compute work in physics. Any of you taking AP Physics C next year? Some of you? Then you're definitely going to know the difference between the two. And then when you multiply two vectors using the cross product, you get another vector. That's how you compute torque or magnetic force. Is it force or magnetic field? I don't know. I had a C- in physics. Anyway, just be aware there's two kinds of multiplication. You don't need to know that tonight. You just got to be able to multiply by a constant, add and subtract. Yeah, well, Mr. Park, it takes kind of long to draw these pictures all the time. Yeah, so is there a better way to work with vectors instead of drawing pictures? Yes. And what is it, physics people? You componentize the vectors. Did you guys componentize vectors? And some of you are going, well, what did we do? Come on, yes or no, did you do this? The inclined plane. The free body diagram. Yeah, that's componentizing vectors. Breaking a vector up into its components. Okay, but this is the way we're going to do it. Okay, so here's the Cartesian plane. So we're going to start off in 2 dimensions. The reason why we study 2 dimensions, even if real life is 3 dimensions, is because it's easier. And then when you make the transition to 3 dimensions, all the formulas will be pretty much the same. So suppose you have a vector that goes from point A to point B. Okay? The coordinates of A are 2, 1. The coordinates of point B, 6, 4. So we have a vector that goes from A to B. So we go like this. So when you do it like this, that means the tail is at A and the head is at B. From A to B. Now we're going to componentize it in the Cartesian plane. So in other words, the vector is going to have an x component and a y component. Now I know you guys in physics, when you do the inclined plane, you're not doing it with the x and y axes, right? You're doing it like to the plane, right? The inclined plane. But it doesn't matter. I mean, you componentize it in some way. So this is the way we do it. How do you figure out the x component? Well, one way to do it is just make a right triangle like this. This distance is called the x component. How do I get that distance? 6 minus 2. So to make sure your vector is pointing in the right direction, you have to go head minus tail. In fact, I'll write it right here. This is called the head minus tail method. That way your vector points in the right direction. So whenever you have a vector that goes from one point to another, just always go head minus tail. 6 minus 2, 4. 4 minus 1, 3. That just means the x component is 4 and the y component is 3. That's what it means. In other words, no matter what point you start at, because remember, vectors can be moved around. No matter what point you start at, you got to go, to get to the head, you go 4 to the right and 3 to the up. That's what this means. So no matter where, like over here, I want to start my vector there. If I want to draw this vector, simply go 4 right and 3 up. And then, boom, that's how you draw your vector. Same thing, right? So as long as you go head minus tail, you'll be okay. Okay, let's do another one. Okay, how about here? This is point C, negative 1, 1. And let's say point D is over here somewhere. Here's point D. What does that look like? Negative 5, 3. Okay, componentize vector CD now. How do you componentize the vector that goes from C to D? Head minus tail. Okay, so this is the head, this is the tail. Negative 5 minus negative 1. Really? Negative 5 minus negative 1. And then 3 minus 1, 2. There you go. That means the x component is negative 4, the y component is 2. That means wherever your tail is, you have to go 4 to the left and 2 to the up to get to the head. So is this the way you guys componentize it in physics? I don't think so. Okay, another way, so mathematicians, we like to use this notation here. But if you're an engineer, they like to use this notation, 4i plus 3j. I and j have hats on them. This one would be negative 4i plus 2j. What does that mean? It means exactly the same thing. It means the x component is 4, the y component is 3. It's just that mathematicians like this one, engineers like that one. So I'm just going to use whichever one I feel like it when I'm typing it in. You got to be able to do both. Yep. All right, so now we know how to componentize vectors. So now can we do basic operations? Yeah. So now we don't even have to draw pictures anymore. That's why we componentize. So if this is vector AB, what do you think 2 times vector AB will be? I mean, if you just have to guess. Yeah, you just multiply each component by 2. So 8, 6. Doesn't it make it twice as long if you did that? Yeah. So to multiply by a constant, just simply multiply each component by that constant. It's very simple. It's kind of like matrices almost. What about adding vectors? Well, if this is AB and CD, what do you think AB plus CD is? And I know you did this in physics. Okay, here are the 2 vectors in component form. If you just have to guess, how do you think I'm going to add them? You add the x components, 0. Then you add the y components, 5. Now, can you visualize this vector? Okay, think of a starting point. To get to the head of the vector, I got to go 0 left and right, and then 5 up. So isn't it going to look like that then? Just pointing straight up? Yeah, that's why component form is so good. You don't have to draw pictures anymore. Okay, what about subtracting? What about vector AB minus CD? What do you think? You subtract the components. 4 minus negative 4. 8. 3 minus 2. Can you imagine what that vector looks like? So wherever your starting point is, you go 8 to the right and 1 to the up. So that means it looks like this, 8 to the right, 1 to the up. Bam! That's what the vector looks like. Component form, it's so good. Now what about the length of the vector? Well, look at this picture right here. If you make a right triangle, this is 4 and this is 3, what would the hypotenuse be? 5. Oh, so Mr. Park, we can just use the Pythagorean theorem then. These are like, the components are just like the sides of the right triangle. So to figure out the length, you simply like use the Pythagorean theorem. Yeah, so if you want a formula, let me squeeze it in here. So if you have a vector in component form, a comma b, how would you find the length? That's what you guys use in physics, right? This is not absolute value now. When you put bar, this is not determinant either. See, you got to use it in context. When you have bars with numbers, that's absolute value. When you have bars with a matrix, that's the determinant. When you have bars with a vector, that means the length or the magnitude of it. See, like if that's velocity, magnitude of velocity is speed. Anyway, it's the square root of a squared plus b squared, right? Because, come on, if you have a right triangle, if this is a and b, Pythagorean theorem, isn't that the hypotenuse? So now, yeah, so again, no need to draw a picture. Okay, so here's AB plus CD. Let's go over here. Oh. So, AB plus CD is that. What is the magnitude of AB plus CD? What is the length of this vector?
5.
It's the square root of this squared plus this squared.
5.
5, isn't it? Okay, what would be the magnitude of AB minus CD? Well, here's the component form of it. So what would the length of it be? Square root of this squared plus... Don't you guys do that in physics? I know you guys do. Yeah, but that was 3 chapters ago. Square root of that squared plus that squared. Root 65. No need to draw pictures, but if you want to draw a picture, then you do this. Okay, this vector means go 8 to the right and 1 to the up. Boom. Same thing, right? So those are the basic computations for vectors. That's what you got to know tonight. Now, once you get started with 2 dimensions, of course, what's the next step? Go to 3 and then higher dimensions. So the next time we have extended, is it next week or the week after? Wait, next week? I know next week Friday there's no homework, right? Because it's no homework weekend. And then when we come back, maybe we have extended.
Yeah.
We're gonna watch Flatland. Gosh, my memory is just getting bad. Flatland. Have you guys read the book Flatland? It used to be required reading for geometry honors, but I think Mr. Masadanga just took it off the list because students weren't reading it over the summer. Anyway, this book teaches you, basically it's about people that live in a 2-dimensional world. You know what 2 dimensions is? XY plane, like a flat surface. Can you imagine beings that live only in the plane of this chalkboard here? Like triangles, quadrilaterals, hexagons. Their whole universe is just only living right here. So if I'm standing here, could they even see me? No, because they only can see in their world. They only can see things in this plane. If I'm not in the plane, they can't see me. But what if I put my arm in? Can they see me now? Yeah, but they're just going to see a cross-section of my arm. See, just like us, we're in 3 dimensions. What if a 4-dimensional being visited them or us? See, like I'm a 3-dimensional being. If I want to visit them, I have to go into their world, but I could easily come out of it too. So if a 4-dimensional person tried to make themselves appear to us, they would do the same thing, except we would only see a cross-section of what they really are. But the cross-section is 3-dimensional. You know what I'm talking about? So this book or this movie that we're going to watch, it kind of teaches you about 4 dimensions and higher even. Because some people just can't even visualize or even think about it. Okay, so we know that's all you got to do, basic operations on tonight's homework. Okay, but now we got to apply it to 3 dimensions now. So how do we even, what is 3 dimensions? Well, space, this, we live in 3 dimensions. This is 3 dimensions. So if we want to set up a coordinate system, it looks like this, right? X, Y, and then now we need an axis perpendicular to both of these. Wait, let me get some pens. I need some pens here. Oh, I only got 1 color and a pencil then. Okay, here, let me show you the progression. This is called 1 dimension. Can you imagine beings that live in only this 1 dimension? They could be points, they could be segments. That's all they can be, either points or segments, right? In fact, the movie we're going to watch, there's beings that live in 1 dimension. Line land, they call it. So, can you imagine? You only can move like this. That's it, that's their whole being right there. Okay, so 2 dimensions is, to get 2 dimensions, you need an axis perpendicular to this one. And now we call that the y-axis. So now we got, this is a plane, the xy plane. Beings that live in a plane. But what about 3 dimensions? Now we need a z-axis. So we need an axis perpendicular to both of these. Where would that be? Like this then, right? We call this the z-axis. Did you guys do some of this in geometry honors? Usually they say yes, because I think there's a page in there. See, but what's the problem? How do you draw 3-dimensional things on your 2-dimensional paper? What do? You gonna tape up a toothpick or something? A popsicle stick? Duct tape, make it, or glue? No! So, how do we draw 3 dimensions then? Well, there's many ways to do it, but this is the standard way in mathematics. Like if you look in the math book. Like this. X, Y, Z. That's the positive X, the positive Y, and the positive Z. Now, I know what some of you are thinking. Mr. Park, can we just say, okay, here's positive X, positive Y, and positive Z comes out like this? Yeah, we could, but that's not the standard way in mathematics. That's the standard way. You guys see that? Yes or no? It's like you're looking into the corner of a room. See, this is the first quadrant right here. See, X and Y positive, and then the Z-axis going up like that. All right, so now how do you plot points? Like for example, how do you plot the point 4, 3, 2? Well, okay, let's go back to this one. You go 4 on the X, you go 3 on the Y, and then you got to go 2 on the Z. So you got to come 2 out like that. So tape up a toothpick with a marshmallow at the end. Yeah, but we're going to draw it on your paper. We're not going to glue things together. So what do you do over here? You go 4 on the X, 3 on the Y, and 2 on the Z. Right there. That's the point. See? 4 on the X, 3 on the Y, 2 on the Z. What's the problem with that though? You can't really tell where that point is. That's right. So you know what we do? We draw a box. We draw a box that's 4 by 3 by 2. Ah, that's an ugly picture. There. The box is 4 by 3 by 2. So there, that's like the opposite. So if this is the origin, then that's the opposite corner of the box. Right there. Now it's easy to see. So these are the kinds of tricks we use to draw graphs. Because like I said, we're not going to tape up toothpicks and things like that. Oh, so wait a minute, Mr. Park. So how do you draw the vector? See, that's how you tell the difference between a point and a vector. See, when you put these things around it, that's not a point anymore. Now it's a vector. So how would you draw a vector that has an x component of 4, a y component of 3, and a z component of 2? Here, I'll show you. Go from the origin to that point you just graphed. See, because look, 0, 0, 0 is the origin. This point is 4, comma 3, comma 2. How do you componentize a vector? You go head minus tail. 4 minus 0, 3 minus 0, 2 minus 0. So basically this vector is forming the diagonal of the box. See? That's how we do it in 3 dimensions. Now, so how do you think of 4 dimensions, Mr. Park? Well, okay, here is the positive z-axis, like this, right? To go to 4 dimensions, you need another axis perpendicular to all 3 of these. So where would you put it so that it's perpendicular to all 3? Like that? No. Where would you put it? See, you can't imagine it because you guys only think about 3 dimensions. You have to think 4 dimensions to be able to place it. You can't put it in 3 dimensions. It's another dimension. But that's where it would go. It would have to be perpendicular to all 3 of these. Think about that this weekend. So now that we're in 3 dimensions, like I told you, the reason why we study 2 dimensions first is because all the formulas are going to be the same. So let's review some formulas. What is this formula? What do we use this for? This is the midpoint formulas in 2 dimensions. So what do you think it looks like in 3 dimensions? Okay, let me tell you. There it is. That's the midpoint formula in 3 dimensions. That's how you find the point that's halfway between 2 other points. What is this formula for? What is this? What do we use this for? The distance formula. This is how we find the distance between 2 points in the Cartesian plane. So how do you think we're going to find the distance between 2 points in space? Whoa. That's why we study 2 dimensions first. And then what if you're in hyperspace, 4 dimensions? Even though you can't imagine it, you can still do computations like, how do you find the distance between 2 points in hyperspace? Then you would just do this. There. Even though you can't imagine it, you can still compute the distance. You know what I'm talking about? Okay, but we don't want to explode your brain. So we'll just stay in 3 dimensions. Okay, what about this formula? Oh, I'm not going to even tell you what it is. We used it last chapter. It's going to come up again in this chapter. What do we use this for? The distance between a point and a line in the Cartesian plane. So, how do you think I'm going to find the distance between a point and a plane in 3 dimensions? Well, I'll tell you. There. This is the distance between a point and a plane. That's because, see, some of you are going, what's going on? In 2 dimensions, what is this graph? A line. In 3 dimensions, what is this graph? It's a plane. It's not a line. It's a plane. All right. What about this? In 2 dimensions, what is this? I'll make space up here. What is this graph in 2 dimensions? It's a circle. Okay, now wait, I'll just see if you guys can think. What is the same graph in 3 dimensions?
A sphere.
No. A sphere would be this. That would be a sphere. The center of the sphere, 1, 2, 3, and the radius would be 5, just like in 2 dimensions, right? Okay, but if I take this away, what is the graph of that in 3 dimensions? Okay, well, think about 2 dimensions first. In 2 dimensions, This is a circle, center at 1, 2, radius 5, right? But see, there's no z in this equation, so z can be anything. So if you are in the xy plane, like if you are in this xy plane right here, isn't the z coordinate 0? Okay, so what if the z coordinate was 1? You would still, so in other words, if I'm 1 unit above the xy plane, you still would have the same circle. 2 units above, still gonna have the same circle. 3, 4, 5, you still have the same circle. So what is the graph gonna be? It's a cylinder, that's right. The graph is a cylinder. But once you put this in, it's a sphere. So, in 4 dimensions, what would this graph be? A hypersphere. Hyper just means one more dimension. That's what it means. It's a hypersphere now. So it's the set of points in hyperspace that are 5 units from a given point. I can't even imagine what it looks like, Mr. Park. Yeah, but you can write its equation, and then you can still study it. So that, again, that's why we do 2 dimensions first, and then you can extend it to 3 dimensions. So look at that, look at number 9 in tonight's homework. Find the center and the radius of that sphere. Well, how do you find the center and radius of a circle? You complete the square on the x's and you complete the squares on the y. So what do you think you're going to do for that? Compute the square on the x's, the y's, and the z's. Okay, so this homework is really easy. And then once we start getting into multiplication, then you gotta really start thinking now. And just remember, there's 2 kinds of multiplication. Those are like 2 separate lessons, because it's involved. So you guys in physics, what did you guys learn about vectors then? Just component. This is all I know, Mr. Park. Well, if this is all you know, I mean, you can do still a lot of stuff. Oh, if you have a right triangle, this is h and this is theta, then this is h cosine theta and h sine theta. You probably could get through physics just knowing that. But when you go to like AP Physics C and engineering courses, you gotta know the real vectors, not baby vectors. You gotta know adult vectors. Okay, any questions? Oh, no, we're not done yet. Sorry, I forgot to tell you. Just when I thought we're gonna finish early. Okay, let me give you a problem, because this problem is number 2 on the homework, and it's gonna be on the quiz. I'm just gonna change the number. That problem is always on the quiz. Okay, so let's read the problem. An airplane is heading east at 400 miles per hour. A wind is blowing with a velocity of 50 miles per hour toward the northeast. If the plane encounters the wind, find the resultant speed, in other words, the new speed of the airplane, and the direction. So basically, okay, we have a plane going east 400 miles per hour. But then there's a wind. Now this wind is blowing, on the homework, it's blowing exactly northeast. So you know what northeast is, right? Like 45-degree angle. Okay, but on the quiz, I'm not going to give you just a 45-degree angle. I'm going to say the wind is blowing, okay, let's change the numbers because I don't want to keep these. Let's say it's going 500 miles per hour. Is that reasonable for an airplane? I guess could be. Might use a lot of gas doing that, though. And then it encounters a wind, and that says 50. I'll do 40 then. The wind blows 40 miles per hour. So the wind is going 40 miles per hour. Okay, let me think. From the east, 42 degrees north. You guys ever seen this notation before? So this means from the east, you go 42 degrees north. So east is this way, right? Then you go 42 degrees north, like that. So that would be like, so that means this angle here would be 42 degrees, like that. So from the east, you go 42. What if I said east 42 degrees south? What does that mean? from the east, you go 42 degrees south, so that means you're going that direction. Okay, so if this is the airplane, and then it encounters this wind, then what's gonna happen? Isn't the plane gonna kind of be blown off course? So you gotta kind of adjust for it with computers and things like that. So these are vectors. These are velocities, that's why. So if you add the two, remember how to add the two vectors together? This would be the new vector. We call that the resultant vector. I'm sure you guys said that in physics. So you see the length of this third arrow here? That is the new speed of the airplane. Can you see that the airplane is going to speed up? Because there's a component of wind blowing this way, right? So yes, the plane is going to speed off, but it's going to be blown off course a little bit. So what you have to do is you have to find the new speed of the airplane and the new course. So how do you do that? Well, there's two ways you can do it. What time is it? One way is to just use trigonometry. Hey, Mr. Park, this is a triangle. So I know that this is 500, this is 42 degrees, and this is 40, right? Because that's the speed. Is there a way I can find the length of this third arrow? Yeah, if you know two sides of the triangle and this angle, well, if this is 42, what's this one right here? 138. If I know two sides and the included angle, how do I find the third side? Oh, cosines. I thought we could purge it already. No. X squared is equal to 500 squared plus 40 squared minus 2, 540 cosine 138 degrees. Punch that in on your calculator and square root it. That's the new speed of the airplane. Now what about the direction now? Is there a way I could figure out this angle right there? Yes. How do I figure out that angle? First of all, can I use the law of sines? Remember, when do you use the law of sines? When you know two angles. Do I know two angles here? No, you only know one angle. But remember what I told you? I said, if you know that the angle for sure is acute, can you stake your life on it that this angle here is less than 90 degrees? Yes, then you can use the law of sines. So to compute this angle, you would go sine phi over, or whatever you want to call that angle. What's opposite from it? 40 equals sine of something over, well, the only other side I know is 500. Wait a minute. What are we trying to do? What am I doing? Sine theta over 40 equals sine of 138. That's the only other angle we know. And what's the opposite side? X, which you stored on your calculator. Remember, do not use a rounded value in another computation. Anyway, then I'm not going to do it, but you guys know how to compute that angle from there, right? Because we took the test on that already. So yeah, there, I got the speed. The new speed is X, and theta. Once you get theta, whatever it is, what do? From the north, you go theta, that's not theta, phi to the east. Sorry, that's wrong. From the east, you go theta north. My goodness. So that's one way to do it. But most people, when they come from physics, you know what they want to do? They want to componentize the vectors. So if you have a vector like this, how do you componentize this one? It's pointing directly to the east, and it's 500 units long. Wouldn't that be 500 comma 0? Right? To get from this point to this point, don't you go 500 to the right and nothing up and down? Okay, now how do you componentize this vector? Well, it's 40 units long and it makes a 42 degree angle. So how do you componentize it? 40 cosine 42, 40 sine 42. So that's it. 40, why am I writing it again? I just don't know. So that's how you componentize that vector. Now, how do you add two vectors together? So you add the x component. So I'm not going to do it. You guys would punch this in on your calculators. That would be the new x component, and the y component would be this plus this. There you go. So this would be this new vector right here. How do you find the length of it? Which would be the speed of the airplane. How would you find the length of this vector? Okay, if I call this A and B, We just did this 15 minutes ago. Square root of a squared plus b squared. This will be the new speed of the airplane. Remember, if you have a vector in component form, how do you find the length? Square root of that squared plus that squared. Now, how do I get this angle? Well, when you componentize this vector, see what you did is you added this, and then you added that. So it's like, it's this and this. It forms a right triangle, basically. How do I find that angle? Tangent theta equals opposite over adjacent. So that would be this over this. Didn't you guys do this with kinematics to find the angle? What's kinematics? All right, these are just basic operations with vectors. It gets more fun when we do multiplication. Okay, only got 2 minutes left.